So this lecture is going to cover 8.6, 8.7, and 8.8 in our textbook. Looking first at section 8.6 and 8.7, I'm going to go ahead and combine those two because they're basically just looking at the integration strategies we've looked at so far and then other methods of integration. So we're kind of just summing up the techniques. There are a lot of different techniques for integration because, again, unlike derivatives where you have product rule, quotient rule, chain rule, and you can always take a derivative directly, you can't necessarily always do that with an integral. So the first thing you want to do when you look at your integrand is you want to think, can I just integrate this directly without doing anything at all? And if not, kind of go through this list. First, check to see if you can simplify the integrand somehow by using maybe some algebra or a trig identity. If you don't see anything right away, see if a simple u substitution would work, because u substitutions are our easiest form of substitution. If you don't see a u substitution that would work, look for some specific forms. And when we say specific forms, this is what I'm talking about. If you have a product of two functions, you can try integration by parts. If you have a rational function, you can try partial fraction decomposition. If you see a square root, maybe a trig substitution. If you see a product of trig functions, then look at the methods we had for dealing with products of trig functions in the section on trig integrals. If you have a higher power of a trig function, try a reduction formula. Look for some special forms, such as, does it look like an inverse trig function integral? Is it like a cosecant or a cotangent? And then in the special forms, we have this table of integrals, and that's what we're going to talk about today. We haven't seen the table of integrals in the previous section, so I'll introduce it in this section here. If none of those work, you can try maybe some unusual substitution. And if none of these work, that's where we'll look at another method in 8.8. First off, let's look at these table of integrals. So the table of integrals can be found at the end of your textbook, or if you go into MyLab Math, under chapter contents, scroll down to ebook resources, and then you'll see table of integrals, and there's a link to the table of integrals. There's hundreds of them. Let's look at just a few examples. In example 1, I want to evaluate this integral. Now, when I look at 1 over 1 minus cosine of x, I can't see how to integrate this the way it's written. If I try a u substitution on the 1 minus cosine of x, I'll end up with a sine x, and something will not cancel. So I can't write everything in the form of u. So what I'm going to do is I'm going to see if I can maybe use trig and algebra to rewrite this integrand. It would be nice if instead of 1 minus cosine, I had 1 minus cosine squared, because then I know that would be sine squared, and I can reduce the denominator of this fraction from 2 terms to 1 term. So what I'm going to do off to the side is I'm going to show you what I mean. So like if I took 1 over cosine, 1 minus cosine of x, sorry. If I took that integrand, and if I multiply it by its conjugate, 1 plus cosine of x, over 1 plus cosine of x, then notice that this is going to be equal to 1 plus cosine of x, but the denominator becomes 1 minus cosine squared x, which in turn will turn into sine squared of x. And that's actually very nice, because once I have sine squared of x, I have a single term in the denominator, and I can break this up into 1 over sine squared x plus cosine of x over sine of x, or sine squared x, sorry. first part would be cosecant squared plus, if you look at cosine over sine, that's cotangent, and 1 over sine is cosecant. So this turns into cosecant cotangent. So cosecant of x, cotangent of x. Okay, so this integral, I've done all that algebra off to the side, so I'm just going to rewrite my integral as the integral of, and I'm going to write this in two pieces. First piece is going to be cosecant squared x dx plus the integral of cosecant, of x cotangent of x. I'm kind of squishing this all in, aren't I? And now when I look at this first integral of cosecant squared is going to be negative cotangent of x plus the integral of cosecant cotangent is going to be negative cosecant, so this becomes a minus cosecant of x. And I'm done. I just need my constant. So in this case, I used a little bit of algebra by multiplying by the conjugate and recognizing that 1 minus cosine squared would use a trig identity, and that would give me sine squared. I could reduce the denominator to one term and kind of play around with it that way. All right, so let's look at another example. In example 2, I'm going to evaluate this integral. So the first thing I notice is that if I rewrite this integral, I can write it as x to the negative 2 times tangent inverse of x dx. My first instinct is to use integration by parts because I have a product of two functions. So I could maybe let u be x to the negative 2 and dv tangent inverse of x dx. But before I do that, what I'd like to do is double check my table of integrals to see if this integral matches up with anything. And when I go into the table of integrals, and just a note, anytime that you use the table of integrals to justify an answer, you need to state which integral you're using. So if I look at the table, and I look at integral number 106 in the table, and I'm going to use the n value of negative 2, it looks like it would work. So let me show you what that integral is. It's the integral of x to the n times tangent inverse of x dx. That's the form of integral number 106, and that's the form I have if my n value were negative 2. So by the table, this is going to be equal to 1 over n plus 1 times, in parentheses, x to the n plus 1 times tangent inverse of x minus the integral of x to the n plus 1 over x squared plus 1 dx, and it's going to be plus some constant c. So here in this particular formula, they tell us that we can use this formula as long as our n value is not negative 1. So sometimes in the table of integrals, you'll have special conditions on your value. So make sure that your integral fits. Now, our n value is negative 2, so there's no problem there. Going back to our integral, and using this table where n is equal to negative 2, our integral is going to be equal to 1 over negative 1, so negative 1, and in parentheses x to the n plus 1 is x to the negative 1, times tangent inverse of x minus the integral of x to the n plus 1 is x to the negative 1 over x squared plus 1 dx. And then we have our constant. So I still have to evaluate the integral portion. I'm going to rewrite this, and I'm also going to get rid of the parentheses by distributing that negative 1. I'm going to clean this up a little bit. and write this as the tangent inverse of x over x. I'm going to make that exponent -1 positive. Minus minus will give me a plus. Okay, and then in the integral, I'm going to drop the x to the -1 down and write this as 1 over x times x squared plus 1 dx, and then plus my constant c. So that looks a little bit better. Now when I look at this integral, I'm saying that maybe I can use partial fractions because I see that it's a rational function and I have a linear and a quadratic factor. It's already factored, which is nice. But again, I'm going to be a little bit lazy and go back to the table and see if I can find an integral that matches to that. And I do. That would be number 85 in the table. So again, I have to state that I'm using the table and I'm using integral number 85. And this particular integral, my a value, which you'll see in just a second, is going to be equal to 1. So in the table of integrals, number 85 is the integral of 1 over x times parentheses a squared plus x squared dx. And that looks like my integral if a were equal to 1, because mine is x times in parentheses x squared plus 1. That's going to be equal to 1 over 2a squared times the natural log of absolute value x squared over a squared plus x squared plus c. Again, going back to my integral and putting all of this together, this is going to be equal to, I still have that negative tangent inverse of x over x. So negative tangent inverse of x over x plus 1 over, my a value is 1, so 2a squared is just 2 times the natural log of the absolute value of x squared over 1 plus x squared plus my constant c. And that's it. Now let's move on to our section 8.8. If all else fails, what we're going to be using is what we call numerical integration. Now, I don't know if you remember from Calculus 1, if you remember Riemann sums, where we were breaking up integrals into areas of rectangles, and we were approximating the integral by adding up the area of these rectangles. So that's what numerical integration is. Again, this is the last resort because, for one, it's super tedious. It's kind of a pain. And it's just an approximation. It's usually not the exact value. It's usually an approximation. Sometimes it will give you the exact value. It just depends on the integrand and the approximation that you're using. So normally what we do is to approximate an integral by breaking the region into rectangles or other common geometric shapes where we can figure out what the area is. So we'll be looking at 3 today. We're going to first look at rectangles, then we're going to look at trapezoids, and then we're going to look at parabolas. Okay. Then what you would do is you would sum or add the areas up. So remember, that's what our Riemann sum is from chapter 5. And when using this technique, there is going to be some error, usually. So when we talk about error, we usually talk about 2 types of error, absolute and relative. Absolute error is sometimes called the actual error. And that's just the difference between your approximation. So in this particular case, if our approximation C is our computed numerical solution, which would be the approximation, And our exact solution is our x value in this formula. Then when we look at the formula and you take the difference between the approximation and the actual, and we always want the absolute value because when we talk about error, we're only looking at 0 or positive, not negative. Then when you take the absolute value, that would be the actual error. So that's just the difference between your approximation and your actual value, or you could look at it as the distance away from the actual value. Now, when we look at relative error, we call that the percent error because it can be written as a percent. And all you're going to do is take your actual error, divide it by the actual absolute value of your actual answer, and then that will give you some decimal approximation usually. Sometimes it will give you a whole number that you can turn into a percent. Let's look at the first method that we're going to use is called the midpoint rule, and that's based on the Riemann sums. Recall from Riemann sums, you can compute using the right, the left, or the midpoint in each subinterval. The midpoint is typically the most accurate, so we're going to use the midpoint rule. And there's a lot of notation here, but basically you're going to have some integral, and the integral is going to go from some a to some b value. The integrand is your f of x. Rooster's going crazy outside. So we're going to use this upper formula that says the midpoint given our n value. N is how many subintervals you partition your whole interval from a to b is. So n is just some number, and it tells you how many pieces you're going to have in your interval from a to b. So the midpoint, giving the n number of subintervals, is going to be the function evaluated at m sub 1. So m stands for midpoint. So that's going to be your first midpoint times this delta x plus f of m sub 2, that's your second midpoint value, times delta x, and so on until you reach your last midpoint value times delta x. Now there's also this summation formula that you can use, and that's just an alternate way to write that midpoint formula from above. But I'm going to use that longer form that we just looked at. This is much easier to use. So notice that you have to figure out what delta x is in order to use the formula. And this is your delta x. So again, that little triangle is the Greek symbol delta. When I think delta, I think distance. So that's saying the distance between your x values can be computed by taking b minus a over n. And I'm going to ignore the rest of that notation. We're just going to go, oh my God, that rooster's so loud. We're just going to go ahead and use this in example 1. So in example 1, we want to approximate the integral, and we're going to use the midpoint rule. Here our n is going to be equal to 4, so we're going to partition our interval into 4 subintervals. So in the integral, the 2 is your a value, and the 6 is your b value. The first thing I'm going to do is I'm going to compute my delta x. Delta x is going to be equal to b minus a over n. In our case, b minus a is 6 minus 2 over n is 4. So our delta x is 1. Okay, going back to the formula, I figured out what this delta x is. Now I have to figure out what f of m sub 1, m sub 2, m sub 3, so on is. So your m sub 1 is going to be your first midpoint point. Notice that we're starting at 2, we're ending at 6. Our delta x is telling us the distance in each interval. So if I start at 2 and I add my delta x, I'm at 3. Add my delta x, I'm at 4. Add that delta x, I'm at 5. Add delta x, I'm at 6. So each one of these subintervals has a distance of a delta x of 1. So in each one of these subintervals, the first interval will be from 2 to 3. There's going to be a midpoint. those midpoints are your m sub 1, m sub 2, m sub 3, and so on. So notice in my first interval, the midpoint between 2 and 3, my m sub 1 is equal to 2.5. In the second interval, my m sub 2 is equal to 3.5, and so on. Well, what we're going to do is we're going to go up to our function at the midpoint, and we're going to draw ourselves a rectangle, and the sides are going to correspond to the endpoints of each interval. So if I go to my next midpoint of 3.5, go up to the function and draw my rectangle. So again, all we're doing is computing, we're creating rectangles and we're going to compute the area of each, add them all up. My next midpoint corresponds to the graph here, and then draw my rectangle. Last one, draw my rectangle. So before I even add up the areas of these rectangles to compute or approximate my integral, notice that I have a little bit of error here. I have an underestimation, and then I have an overestimation, an underestimation, an overestimation, and that's where my error is going to come from. So let's look at our m sub 1 at 2.5. It's going to correspond to a y value of f of 2.5. And the next one will correspond to a y value of f of 3.5, and so on. So when I compute the area for each one of these rectangles, it's going to have a base of delta x, and in our case our delta x is 1, and it's going to have a height of the f, in this case, for this first rectangle, the height is going to be f of 2.5, because that's the y value at this point. All right, so let's put all this together and compute the midpoint, where our n value is 4. So it's going to be f of 2.5 times our delta x of 1 plus f of 3.5, our delta x is 1, plus f of, the next one would be 4.5, times the delta x of 1 plus f of 5.5, and that's our last one, delta x of 1. All right, so now all we have to do is figure out, sorry, I'm getting a little bit of a tickle in my throat. We just have to figure out what all these values are for my f values. Now, if I can just compute this whole thing in the calculator at one time. Something else I wanted to note is that when multiplying by 1, that's not going to change. Also note that each one of these terms has that common factor of our delta x of 1. So we could have factored out that delta x, figured out the sum, and then at the end multiplied by delta x. But now putting this into the calculator, I get f of 2.5 in the calculator. Remember, my integrand is negative 0.2x squared plus 1.2x plus 2.2. That will give me 3.95. And now these are exact values. The next one will give me a 3.95 as well. The next value is going to be 3.55. If you find that these values, these intermediate values, are very long decimals, I would suggest not rounding and putting the whole thing in the calculator in one move. Last is 2.75. So in my calculator, I get that the midpoint approximation for this integral is 4.2. Now I can figure out the actual value of this integral from 2 to 6 by simply putting it into my calculator. When I figure out the actual value, I get 14.1 with the 3 repeating. So I'm going to write this as 14.13 bar. So notice that my approximation, 14.2, it's a little bit under, or a little bit over, sorry, the approximation of 14.13 repeating. But they're pretty close. So the absolute error, that I'll just call error, is going to be equal to 14.2 minus the 14.13 repeating absolute value. And that will come out as, exactly 0.06 repeating. So that would be the absolute error. Now the relative error is simply taking that and dividing it by the actual. And it's in the absolute value. Oh my goodness. I'm losing my voice here. All right, so when I plug that into the calculator, I get 0.004 with a bunch of 6 repeating. I'm going to just write that down approximately as 0.0047. So just if you're doing a problem like this on MyLab, just make sure that you read the notation correctly, because it should tell you what to approximate the decimal to. Now, if I want to write that as a percent, I simply move the decimal over 2 places, and the percent error would just be 0.47%. So a really small error. So again, that would be using the midpoint. Next, we're going to use the trapezoid rule. Now, the trapezoid rule is based on the area of a trapezoid. We're going back to what a trapezoid looks like. It's similar to a rectangle, but you usually have one side that's tilted. So you're going to have a height, and then you're going to have two sides that don't have the same distance because it's not a rectangle. So typically we'll use a big B and a little b to indicate those are the two different bases. And then the area for a trapezoid is equal to 1/2. You add the two bases together, and then you multiply by the height. So that's why you see that half in the trapezoid formula in this box here. So we're going to use capital T for trapezoid, given the n number of intervals. So n is still the same. It's just the number of subintervals you have. Then the trapezoid rule is going to be you take half times your first term, and then all the middle terms are just the f of x sub 1 plus f of x sub 2 and so on. So they're writing this in a summation formula. And then half of the last term, multiply all of that by your delta x. So delta x is still the same as it was before. It's still going to be b minus a over n. And here I'm going to be using the exact same integral so we can kind of compare the different approximation methods and see which one will work best given our particular integral. All right, so let's go ahead and write down our delta x. It's going to be the same as it was before. It's 6 minus 2 over n is still equal to 4, so our delta x is still 1. So the partitions are still going to be the same. In this particular formula, our starting point is going to be denoted by an x sub 0. So notice in our trapezoid formula, we have f of x sub 0, that's our first point. And then the next point, if we go our delta x distance of 1, would be the x sub 1, and so on. 4 is going to be x sub 2, 5 is going to be x sub 3, and 6 is going to be x sub 4. And now we're not looking at the midpoint as we did prior. What we're doing is we're just drawing trapezoids for each subinterval. So our base is our delta x. And then when we go from one side to the other, we create a trapezoid that kind of looks like it's standing up. And then we go to our next trapezoid. We have the base of delta x, draw up the side, and then connect the two. delta x, up, draw my trapezoid, delta x distance, up, and draw my last trapezoid. Sorry, my hand's kind of wiggly here. It's in an odd angle. Right, so what I notice using the trapezoid formula for this particular integral is it looks like it's going to be an underestimation all the way, right? Because my trapezoids are underneath that curve. So right away I'm thinking this is an underestimation. However, in the trapezoid formula, we're going to need to figure out our f of x sub 0, f of x sub 1, and so on. So if we look at these points along our curve, the first one would be our f of x sub 0, which is 2. So f of 2, f of 3, f of 4, and so on. In our trapezoid formula, so t of n is 4. Remember, the first thing we want to do is we want to take 1/2 times our x sub 0 value. So 1/2 f, oh my 2 looks weird, f of 2 plus, and all the middle terms, and in this case the middle terms are going to be the x sub 1, x sub 2, x sub 3, will not have the half in front of it. They stay exactly as they're written. So this would be f of 3 plus f of 4 plus f of 5 plus, and then 1/2 times the last value, which would be f of 6. We're going to multiply all of that by our delta x, which is simply 1 in this case, so it's not going to change my values. Now I can figure out all these intermittent values, but after I put it in the calculator, I get 14 exactly. I'm not approximating that. So by using the trapezoid rule, the value using 4 subintervals in this particular case is 14, which is an underestimation because remember our actual is 14.13 repeating. Before we go further and figure out the error, what I like to do is go back up to this formula and notice that there's all of this notation, and this notation was also in midpoint, had all this weird notation. That would be if you want to put the whole formula into a calculator. And again, we're not going to cover that because the intervals, our subintervals are very small. We're going to look at in this particular case, we're looking at a subinterval of n equal to 4. So you would normally use your calculator if you're looking at a subinterval like n is equal to 20. You don't want to draw out 20 terms and figure that out by hand. But you're not required to do that. That would just be a waste of your time. I just wanted to give you an idea of how these formulas work and how you can use them to approximate integrals. Right, so let's finish this off. Our actual was 14.13 repeating, so that gives me an error of subtract, take the absolute value, and it's going to be 0.13 with the 3 repeating. Now our relative error, if we divide that by 14.13 repeating, I get that it's approximately equal to, I'm going to take this out to 1, 2, 3, 4, I'll go 4 decimal places, 0.0094, and you could check me on that. As a percent, it would be approximately 0.94%. Now notice the error here is larger using trapezoid than it was for midpoint, and that's because the midpoint, there was some overestimation and some underestimation with the rectangles, but with trapezoid for this particular integrand, everything is an underestimation. Let's move on to our last method of approximation. This would be our Simpson's rule. Simpson's rule is really interesting. Simpson's rule is based on parabolas. if you can write a parabola as y equal to some negative b, b, why is it not writing? B over a squared times x squared plus your b value. If you can write a parabola in this form, then the area is simply 4/3 a times b. Okay. And that's kind of what Simpson's rule is based on. It's based on a parabola. So typically, if your integrand, when you graph it, has a lot of curve to it, typically Simpson's rule will work best because you're fitting little tiny parabolas into your curve. And that's also why when we look at Simpson's formula, we have not just a delta x, we have delta x over 3 because that comes from the area formula. And then also look at the intermediate terms. The first term stays the same, but the next term is 4 times the f of x1 or y value. And then you alternate to 2, 4, 2, 4, and so on. So the middle terms are 4, 2, 4, 2, 4, 2. It will always end in a 4, and then the last term is exactly as written. And to get it in that form, we have to make sure that our n values, which are those equally spaced subintervals, is an even integer. Okay? If it's not an integer, even integer, we won't end up with a 4 at the end. We'll end up with a 2, and the formula will not work. So to use Simpson's rule to approximate, your n has to be even. Now there is this other formula here below. So if Simpson's rule is kind of a pain. So if you did already know what the trapezoid rules were for your n and 2 times n, then you could simply plug that in and figure out your Simpson's rule. We're not going to use that because we're just using an n value of 4. Again, I'm using the same integral, same graph. So with an n value of 4, using Simpson's rule is not a big deal. First of all, we're using delta x over 3. So remember, our delta x is equal to 1. So our delta x over 3 is equal to 1/3. And using Simpson's rule, we start with 2, we end with 6. Our delta x is 1, so we're still using the same points 1, 3, 4, and 5 with that distance of delta x between each one of these. So we have our 4 partitions. Why we need an even amount is because this is kind of how Simpson's rule works. You start out with your first, and then you skip one and you go to the next one. And then this would be like a vertex to a little parabola in the middle, and you draw a parabola. And then you skip one, go to the last. This would be the point where you draw your kind of parabola. In this case, it's kind of a sideways parabola. And since our function is nicely curved, it kind of follows the curve. However, you don't need to know that to use Simpson's formula. All you have to do is find, as with trapezoid, find the corresponding values here and then just plug them into the formula. So the first value, this is our f of 2, f of 3, same as trapezoid, f of 4, and so on. In the Simpson's rule formula, S of, here we're using 4 subintervals. So remember, the first thing we want to do with Simpson's rule is take f of 2, that's our first point, plus 4 times f of 3 plus 2 times f of 4 plus 4 times f of 5, and then our last would stay the same as f of 6. We're going to multiply that by our delta x over 3, so that would be multiplied, all of it multiplied by 1/3. Sorry, I'm going to close my grouping symbols. And now when I put that in the calculator, I get 14.13 repeating. Remember, this is supposed to be an approximation using Simpson's rule, but it actually turned out to be the actual value as well. So by using Simpson's rule, my approximation is actually equal to the actual value. So both the error, which is 0, and the relative error, which is 0%, they're both 0. So why? The reason why is because when you look at this integrand, my integrand is a parabola. So Simpson's rule gave me an exact value for this particular integrand. Those are our 3 methods for approximation. Again, they're super tedious, and they would be used as a last resort if none of the other integration techniques worked. I'm going to just mention this theorem 8.2. And if you'd like to learn more about how you can use errors in the 3 methods of approximation, then you can just go ahead on YouTube and watch the full video for 8.8. It's called 8.8 Math 242. So that would be in the same playlist as all the other videos are in. What this does is it tells you a bound on the error. So if you have, and here the subscript M stands for midpoint, the E is for error. So the error using the midpoint formula is going to be less than or equal to all of this stuff. And we're not going to go through how you use this. But then if you use trapezoid, your error will be less than or equal all of this stuff that you would compute. And if you use Simpson's rule, that error will be less than all of this stuff. So why this formula is important is, let's say that you want to approximate your integral, but you want your error to be less than a certain amount. Well, then these formulas will tell you how many subintegrals you need. Okay, so that's it for all of this.